Hey guys, it's Finn. In this video, I'll talk about the gradient vanishing problem. You have already seen this slide probably in one of the previous videos. It's taken out of the backpropagation video. I had to take a screenshot of this slide because I deleted my presentations, and so you can see there's a little arrow in there. So yeah, that's like my arrow, and I had to take a screenshot of YouTube, but I hope you can ignore this. So what we had in the top left is we had how we thought how we could derive one error signal. So for example, for an output neuron, it's the just a simple example. We have the actual output minus the target output, which could be an error, and the error for any hidden neuron. Usually, this error is also referred as a gradient. So in the future videos, I will talk about it as the gradient, or like it's the same. Error and gradient, for me, it is the same. Some videos explain it differently with other terms, but I want to call it the gradient for any neuron. So the gradient, for example, of this neuron is equal to the sum of the wakes times the gradient of these neuron. And this is like intuitive, this makes sense. But we figured out that this is partially true, but we also need to multiply it with the derivative of the output function. And this is where the gradient vanishing problem occurs. So this is like the in the bottom right, we have the error signal or gradient for any neuron is equal to let's say we have an inner neuron is equal to the sum of the error signals in the layer before times the weights. And this one is the derivative of the sigmoid function. We can plug any function in here, and we might have different derivatives. But so this is specifically for the sigmoid function. If we have, for example, the ReLU, we might just have 1 or 0 in here. So yeah. The problem I've shown to you, I've shown you this in another video, that this term for the sigmoid function has a maximum value of 0.25. So this means, let's say we have got a gradient. Let's say we have a gradient of 1, which is very unlikely, but we might have a gradient of 1 here. In this case, we had 0.9 and 0.1, or like let's say the intuitive error, the difference is 0.9 and 0.1. But the first thing we need to do is we need to multiply it by the derivative, and this one, the maximum value of that is 0.25. So let's say the actual gradient at these places or at these neurons can have a maximum value of 0.25. Now let's go one step back, and we're going to have the sum of for example, let's take this neuron. We have the sum of the wakes times the gradients. So let's say the wakes are roughly between -1 and 1. So we are going to have a maximum gradient, or maximum without the derivative right now, a maximum gradient of this would be 0.25, 0.25. We're going to add this one up, 0.5, and then we need to multiply it with the derivative of the output again. So we are going to end up with 0.25 times 0.5 at max, and this is equal to 1/8. So the gradient at this is maybe 1/8 at max, and if we keep going back, this is going to become less and less and less. So the huge problem is that we need to multiply to get the gradient, we need to multiply the difference with the derivative of the output function, or like the sum with the output function, with the output derivative. And what we want to do is, we can't change this formula, this is fixed. But what we could do is we could take a activation function where this term, the derivative, is like maybe static or very close to 1, that the gradient does not vanish. And as an example, I've shown to you the ReLU function, or the leaky ReLU. And this is pretty much how to think about the gradient vanishing problem, that you can simply think about it, or you just need to look at the formula and see, okay, we are going to multiply it with the derivative of our output neuron, or with the derivative of the output of our neuron. So if the derivative is always below 0.25, we are going to reduce and reduce and reduce our gradient each time we iterate back in our network. And yeah, for solving this, we just need a activation function with a gradient that is close to 1. And as I said, we have the ReLU and the leaky ReLU in this for this. And yeah, I hope you understood this. If you have any questions, just ask me in the comment section, and I hope to see you in the next video.